Hello, my name is Franco Matkin and I'm a PhD student at the Research Institute for Signal Systems and Computational Intelligence in Santa Fe, Argentina. Today, I'll be presenting our work named Cranial Implant Design via Virtual Craniectomy with Shape Priors, made for the Autoimplant Challenge. This work was made in collaboration with researchers from University of Cambridge and Imperial College London. Cranioplasty is a surgical procedure aimed at repairing a skull vault defect by insertion of a bone or non-biological implant, for example metal or plastic. Such skull defect may exist due to different reasons, like a brain tumor removal procedure or a decompressive craniectomy surgery following a traumatic brain injury. Cranial implant design is usually performed by experts using computer-aided design software specifically tailored for this task. Here we focus on reconstructing the flap only, on skulls extracted from high-resolution and anisotropic computed tomography images. The Autoimplant Challenge, organized for the first time at MICAI 2020, aims at benchmarking the latest development in computational methods for cranial implant reconstruction. That's why in this work we evaluate two approaches to solve this task using deep learning models. For the challenge, the organizers selected 100 images for training and 110 images for testing from the CQ 500 public database. From the 110 test images, 100 of them have simulated surgical defects, which follow the same distribution as the one on the training images, labeled in our work as D-test, while the remaining 10 have defects which do not follow with the same distribution, labeled as D-test extra. The images have fixed dimensions in the axial plane and are variable numbers of axial slices. Our work presented in MICAI this year proposes a simple virtual craniectomy procedure, which enables training different deep learning models in a self-supervised way, giving a dataset composed of full skulls using two different approaches, direct estimation of the implant or reconstruct and subtract. Following the conclusions of this work, we decided to only use the direct estimation approach, since the latter one tends to generate more noise in areas far from the flap. Even though this method could work in low-resolution real craniectomy images, we wanted to avoid a pixelated surface when going back to the original dimensions, as the authors of the baseline approach showed with the coarse approximation. So we adapted the virtual craniectomy procedure to account for flap shapes that are similar to the ones introduced in the Autoimplant Challenge, and changed some stuff for making it work in higher resolution images. The virtual craniectomy procedure was adapted from our previous work, and besides extracting spherical and cubic shapes, a custom template was used to match the craniectomies of the training dataset. By observing the data, we noticed that defects tend to follow a pattern given by the intersection of the skull with a cube with two cylinders over the edges perpendicular to the axial planes. So we designed a variable-sized template shape which produces similar defects. The virtual craniectomy was used as a data augmentation mechanism to generate a variety of training samples from a limited amount of full skulls, resulting in a self-supervised learning approach, where no annotated skull defects are required for training. During training, we sampled images coming from both sources, simulated virtual craniectomies and defective skulls provided by the organizers. Also, we operate on full skulls, which are rigidly registered to an atlas and resampled to an intermediate resolution. Aligning the images allows us to work in a common space, which simplifies the reconstruction task. Before training, all the images are rigidly registered to a common space of 304 by 304 by 224 voxels of dimension, because it was the maximum size we managed to fit in GPU memory. We used FSL Flirt software package for rigid registration. At test time, given a test effective image, we apply the same registration procedure, which returns a transformation and its inverse. The skull defects are reconstructed in this common space, and the final estimate in the original space is recovered by applying the inverse transformation. Registering allowed us to normalize the images by resampling them to an intermediate resolution and discard eventual regions that are not useful for this particular task. Here we can see how that cropping is performed after aligning the images. Our first method is a direct estimation model which follows the same architecture as the direct estimation unit used in our MICAI work. It is a standard 3D unit encoder-decoder architecture with skip connections, trained using a compound loss which combines dice and cross-entropy terms. Since the direct estimation unit model is a fully convolutional architecture, The receptive field of the model is mainly determined by the amount of layers and parameters of the pooling and convolution operations. That is, the local support of the output predictions is restricted to a certain area in the input image. Because of this, when we have to reconstruct big or out-of-distribution skull defects, it may happen that most of the image support for certain parts of it are background, and the network may have no context to infer the implant shape. That's why we propose to incorporate context via shape priors, giving us an extra channel to the segmentation network. Previous works have shown that this simple extension can boost the robustness of existing state-of-the-art pixel-wise approaches in medical image segmentation tasks. We take advantage of the fact that images are co-registered to a common space and use the same skull atlas as shape prior. After registration, we concatenate the resample image with the atlas as an input channel and train the network following the same strategy discussed before. In this case, the shape prior acts as a kind of initialization for the network's output, providing additional context that will be useful especially to reconstruct out-of-distribution defects. We refer to this model as the direct estimation shape unit. Here you have the results of this same out-of-distribution example without and after incorporating shape priors. We reported the dice coefficient and Hausdorff distance measured in test images, the additional 10 images, and the whole test dataset. Here we can observe how direct estimation shape unit works better for the out-of-distribution cases, while direct estimation unit outperforms the other model in the regular test set. Since the whole test dataset is composed of only 10 images from the out-of-distribution dataset, the direct estimation model shows better performance in the overall comparison. Moreover, direct estimation unit outperforms the two baseline models reported by the organizers. Here we have some qualitative examples. In those cases following the same pattern as the training dataset, both methods performed well. But this doesn't happen in all cases of the split. In this particular image, we can see that even if the direct estimation shape unit model managed to reconstruct the implant, the quality of the reconstruction is lower than that of the direct estimation unit. The opposite happened in the out-of-distribution image, in where the model which incorporated shape priors managed to reconstruct the implant, while the direct estimation unit failed in this task. To summarize, in this work we evaluated two different approaches for cranial implant reconstruction based on deep learning, a direct estimation method and an alternative strategy which incorporates shape priors. We adapted the virtual craniectomy procedure proposed in our MICAI work to the defect distribution of the auto-implant challenge. We found that the simple direct estimation unit method produces more accurate results for the skull defects which follow the same distribution as those in the training dataset. However, for out-of-distribution cases where the direct estimation unit model tends to fail, the use of shape priors increases the robustness of the model, providing additional context to the network. In our implementation, this gain in robustness for out-of-distribution cases was achieved to the detriment of the overall accuracy. In future work, we plan to study alternative ways to introduce shape priors. This is considering deformable registration instead of rigid transformations, or incorporating shape priors in a co-registration and segmentation process. The source code used for this and the previous work can be found in this GitLab repo. Thank you for your attention.